Okay, good afternoon. So we're picking up on some algebra, simplifying rational functions, or dividing polynomials, however you would like to think about it. And I want to start for a little bit with just a step back and take a little description of what's going on here with rational functions and simplifying them. Let's take, for example, let's take a look at a very, very, very important part of what's happening in a lot of algebra, which is the fact that something times 1 is something. Okay. It's a unique power to the number 1 that it can multiply by any number or any expression or anything, and it gives you that thing back. It's called the identity, right? So it's not too far off, and it is in fact quite related in some serious way to the additive identity of 0. So if you add 0 to something, you also get something back. You could think of it in terms of this, like actually multiplying by 1 or adding 0 is trivial to some extent, right? In the sense that it doesn't actually affect the thing you're multiplying it by. You're asking, like, well, what is 1 times this thing? One of these things. How much is one of these things? Well, it's exactly one of these things. So this is kind of key for us. What is more key, and where this really evolves very quickly, is, let's double star, triple star this. Note that 1 and 0 have many forms. Okay, and in particular, let's look at the forms that 1 can take. So we're talking now about equivalent expressions to 1, expressions that are equivalent to the number 1. Okay. Well, think about them. Another way of thinking about this is that you're just looking at things that would simplify, and if you simplified them, meaning maybe you executed things, they would be equal to 1. Well, 1 is equivalent to 2 divided by 2. It's also equivalent to 3 divided by 3. It's also equivalent to, say, 10 divided by 10, or 1052 divided by 1052. The division of something by itself gives you 1. It is an equivalent way of writing 1. And therefore, as well, x over x, or x squared minus 5x plus 12 over x squared minus 5x plus 12. So these two things combined, this first initial statement here that something times 1 is equal to something, combined with this fundamental and core mathematical idea that something divided by itself is 1, is really what we're talking about here with this factoring and dividing to 1. What we're saying is that we can find sometimes in these more complicated expressions, if we factor them top and bottom, we can find a piece that is in fact 1. Right? We can find a piece that is 1, and because now in the process of factoring what we're doing is setting up a distributed multiplication, we know that if part of that distribution is 1, then 1 times something is something. So we can essentially simplify to eliminate those terms that divide to 1. So for example, let's think about setting something up that we can think about, like This is a hijacking to some extent of what the usual process looks like, or a reversal even, where we can now say something like, oh, well, x plus 2 times x divided by x minus 1 is equal to this times, say, x plus 3 over x plus 3, which I think is fine, right? This is 1. So of course it is. This is the statement that something equals something times 1. Something equals that same something times 1. X plus 2 divided by x minus 1 equals x plus 2 divided by x minus 1 times 1. Right? And in fact, let me even step back a step and say, are we comfortable with this statement? If we are comfortable with this statement, x plus 2 divided by x minus 1 equals x plus 2 divided by x minus 1 times 1, and we're comfortable with the fact that 1 can come in infinitely many different forms. They seem a little trivial, right? It's just like, oh, well, just divide something by itself. But that's precisely an incredibly powerful idea, right? 1 can take any form now. So what we have here is, just as a for example, 1 could take that form. And what are the ramifications of this? Well, it's the reversal of what we were doing last week and the reversal of what we'll practice a bit more today. It's that if now we can maybe see that if we were to start with this thing and we were asked, oh, hey, see if you can simplify it to a simpler rational expression, our first step is essentially to look for something that will be a plus 1. I mean, that's really the heart. That is the step in some way. We're trying to look for something that would be 1, and if it's like looks like a more complex version of 1, then it likely arises from a factoring. So if you take this and step through the equal sign from bottom up, we see this degree 2 divided by degree 2, then the factored form, then the grouped form so that it divides to 1, and so we get that as a simplified version of this. Now, of course, this isn't the direction, so we have to pay attention, like here, x cannot be negative 3, because that would make it be 0, but here there's no obvious restriction, so we would have to bring it along with us. So it's this kind of unique thing that we're trying to do here with factoring and simplifying these things. Okay, let's take a look. Let me erase. Oops. Simplify this. Well, now, what are we really looking for? What we're really looking for is, can we rewrite this as an expression, an equivalent expression, that is something times 1. Something simpler times 1. Now, of course, we can say, like, this is equal to itself times 1. That's good. That doesn't help us simplify. So what we're looking for is, can we write this as something simpler times 1? And the way we look for that, the way we explore that question, is in part, and in large part, via factoring. So we're going to factor this bottom piece. I'm looking at x plus 4x minus 3. That is the factored form of this. So what do we know? X cannot be negative 4, x cannot be 3. And that will continue down for the rest of the problem, regardless of what happens. Now, what are we looking at here? Let's do a little reordering. Okay, so just commuting this multiplication, saying it doesn't matter if we multiply a times b or b times a, it commutes. We get something times 1. So what we have basically done is established that this initial first thing can be rewritten as something simpler times a form of 1. And because it can do that, and because we know the identity property of 1 here, that is a simplified version. Maybe you multiply out the top, but there you have it. So hopefully this is getting, a little bit closer to the concept of what we're doing and why what we're doing works. We aren't just we're not able to choose to do this arbitrarily. It has to do with a fundamental and a very, very powerful relationship that 1 has, the number 1 has, in particular that 1 times anything is that same anything. So let's see if we can't find a couple more here. Y squared times y squared plus 3y plus 2 divided by 2y, y minus 4, y plus 2. Simplify this. Let's note immediately, sorry about that. Let's note immediately that y cannot be, we'll do it in red to make it stand out. Y cannot be 0, y cannot be 4, and y cannot be -2. Why is that? If it took on any of those values, the function would attempt to divide by 0, and therefore give us no output. Let's also notice that there seems to be a y incoming on top, right? Sometimes this is a sneaky one because it doesn't quite look like the same factors of like y plus or minus some number, but it is. It's y plus or minus 0, so it's perfectly fine. What do we have here? Let's do it right away. We have this as true. We can almost immediately, in this case, write this semi-factored form in a way that we get this y divided by y going to 1. And so we've already done a quick simplification right there. Let's take it a step further and simplify this top. I think it's going to be y plus 2, y plus 1. So what we get is that this y plus 2's cancel. So you can tell, I like to do this, right? We're going back and forth between this like very, very strategized, coordinated, like do this same process over and over again. Make sure you write this thing out so that you see that it's something times 1. Well, we don't always have to do that, and you won't always see that written out so explicitly. So like in this case where I just divided y plus 2 by y plus 2, I didn't write them directly over each other and to the right as a separate multiplication. So we have to take for granted that we understand a little bit of like, well, there's commutative. I could rewrite this if I wanted to like this. And it's perfectly valuable if you want to do it that way. it's also perfectly valuable if you don't and you understand what the resulting things are here, that y plus 2 has been eliminated on top and bottom. They've divided each other out, and therefore we're left with y times y plus 1 over 2 times y plus 4, where y cannot be 0, 4, or negative 2. It's a good question. Don't hesitate to practice this stuff. It may seem like, oh, it's just something that came naturally to him. That's not exactly true. It is something, sorry, I'm not sure why this is coming up as a box, but it's something that took a lot of practice, a lot of time to really understand at a fundamental level. Let's take a look at another example here. Let's see, which one? Let's take on a pretty complicated one. Let's look at x squared minus 16x plus 64 times x plus 2 divided by x squared minus 64 times x squared minus 6x minus 16. Okay, it looks like there's going to be some things that make the bottom 0, so we will have to worry about that. Usually we see it at the same time as we start factoring. So I'm going to do a bunch of factoring here. So it looks like this top left polynomial x squared minus 16x plus 64, that factors like this. X plus 2 looks like it's already factored. X squared minus 64 factors like this. Okay. There we go. Where x cannot be 8, negative 8, or negative 2. So it certainly doesn't have to be degree 2 polynomial divided by degree 2 polynomial. Here we're talking about degree 3 divided by degree 4, noting that the degree, though it looks like maybe the top and bottom both have degree 2, they don't. Of course they don't, because they need to be multiplied out in order to understand what the degree is. You can add it. There's some rules that you can do. This is 2, say the bottom, say x squared minus 64 times x squared minus 6x minus 16. What we know is that the x squared times the x squared term, when you distribute out here, is going to give you your highest degree term, and that degree will be 4. X squared times x squared is x to the 4th. Let's do one more and pick up on Thursday. Let's do... another layer of complication here. What have I introduced in this problem for us to grapple with? Well, a second unknown variable, z. So this is not a single variable expression, it is a multivariable expression with 2, x and z, but we can factor in the same types of ways that we would if z were a fixed number. Therefore, let's take a look at simplifying here. Let's note here that x cannot be negative z, and it cannot be 3. So let's see here, a little factoring. Looks like x plus 3, that's the difference between two squares. And actually, so is this. Perfectly fine. You might see it written like this. So it is possible to divide out to a degree 0 polynomial on the bottom. Perfectly fine. Just means essentially that the division works very well in the overall sense of the original problem. So, good set of questions to think about. Good idea to get yourself onto like rock steady ground when it comes to understanding, first of all, that any expression times 1 is just that expression, and secondly, that 1 can take infinitely many different forms of something divided by itself. And that is what is in essence what we're doing with this simplification. We're saying, well, can an expression be written as a simpler expression that is something times 1? Then we can eliminate the 1. We don't need to look at it anymore. We know that something divided by something is always 1, even if those somethings are changing together, right? Like a variable does. X divided by x, well, x is not fixed, but x is fixed relative to itself. As x goes up by a certain amount, x also goes up by a certain amount, so x divided by x always going to be 1. So thanks for joining me. See you next time.